Hi, my name is Eldrich Rebello, and I'm with the Wind Energy Institute of Canada. And this is our presentation titled Providing Secondary Frequency Regulation from a Single Type 4 Wind Turbine and a Battery Storage System. Now, that is quite a long title, which is why we have a broad summary right at the top. So, this work provides empirical data showing how a single wind turbine and a storage battery system can be combined to provide the ancillary service of AGC, also known as secondary frequency regulation. I mentioned empirical data right at the top. I'll come back to that in a second. But first, why this is important is because we've used commercially available equipment. So the wind turbine and the battery storage system are both commercial products, meaning that anyone with access to similar systems can replicate and verify our results. This is not a simulation, which is why we emphasize empirical data. This data is often not publicly available, or when it is, it's limited in scope and presentation. So this is an attempt to change that, and our data will be useful. We hope that will be useful for future analysis and also input to other works. A few words about who we are and where the project site is. So WECAN, or the Wind Energy Institute of Canada, is a non-profit research organization located in the province of Prince Edward Island on the Atlantic coast of the country. The project site was east of the city of Regina in the center of Canada. A few definitions before we go ahead. AGC, or automatic generation control, is simply a system for adjusting the power outputs of multiple generators in an attempt to balance supply and demand on the grid. In the context of AGC, this is typically operated as a paid service, if not a competitive market, which is why generators typically bid with what is known as a regulation offer, or in other words, an amount or magnitude of power offered on the market or to the service. Now, you could ask if similar work exists, and it does, but the limitations of many works that are publicly available is one, the amount of data that's made public, and also the duration of that data. So, two examples that we've cited here, one is Enercon's work in Feldheim in Germany. This, however, has limited data. It's a similar situation with the battery from South Australia, which doesn't have data showing how it operates in parallel with wind. This is a single line diagram of the system used in this work. There are two key components, the wind turbine itself and the battery inverter. The wind turbine is an 800 kilowatt Enercon machine. The inverter connects to the inverter controller controls two separate inverters, and the combined storage capacity of the battery is 744 kilowatt hours, and the total throughput is 400 kVA. Note also how our controller interfaces with this system. We do not control the wind turbine. We instead control only the storage battery inverter, although we receive data from several points. This is a attempt to highlight the difference between providing AGC from a conventional synchronous machine, say a coal or a gas generator on the left, versus a wind turbine on the right. You'll see two key differences here. One being that the power output of a conventional generator can be controlled. This is simply because you have control over the fuel input and you can therefore control the power output. AGC is added to the on top of this, which means that if you need to provide a power increase, simply burn more fuel. This is in stark contrast to the situation with a variable generator, say like a wind turbine here, in that the fuel input to this generator is not controlled, which means that the base for something like AGC is constantly moving. So on top of this, you then need to add a variable AGC signal. So this presents a challenge when evaluating work like this. You could ask a couple of questions here. Why use a battery? One of the most obvious answers is we have done work similar to this in the past using only wind turbines. And one of the obvious challenges there is that in order to provide up regulation or an increase in power, you do need to operate the wind farm or the wind turbine curtailed. This is often not as beneficial because you're losing constant generation and the return depends on how much you are paid for AGC performance. The other aspect is that a battery has finite energy capacity. And although you can use a battery alone to provide AGC, it is often easier in terms of maintenance and wear and tear to combine the battery with a generation source like a wind turbine. The algorithm we've used here is fairly simple. It has two broad inputs, one being historical AGC data, and the second being live wind speed data from the wind turbines in a cell anemometer. Now, we use live wind speed data, average it, and then use a turbine power curve to estimate what the wind generation would have been at a certain point in time. Now, we then correct for the error between this predicted value and the actual measured value here, and then add on the historical AGC targets. These, when combined, become the input to the battery controller. So as you can see, there's not a lot going on here, and the algorithm is fairly simple. Now, in summary of the test results that I'm about to show you, there are two sets of data. One is we began with operating the battery alone to establish a baseline for how well it can perform. Now, unsurprisingly, using an inverter-based system with stored energy, you get fantastic performance. The second aspect of this is adding the turbine in parallel. The one input we use here is historical AGC data. Note that this is historical, it's not live data. It's updated every 4 seconds, and we've suitably scaled it to match our regulation bids. So when the battery was operating alone, we've used a regulation bid of 400 kilowatts, or split as 200 up and 200 down. This lasts 30 minutes. And when you combine the battery and the wind turbine, we change the regulation bid to 80 kilowatts. That's 40 up and 40 down. This lasts 4.5 hours. It's important to note here that the wind turbine was not curtailed, so it is free to track maximum power at all times. We have measured performance using two metrics, one being the NRC method of the National Research Council of Canada and PJM's method. Other methods are also available, notably Cal ISO's performance score metric. However, we have not used that here. The first set of results, exactly as you'd expect, with the battery operating alone, providing the full AGC, it performs with very accurately with limited error. The only aspect to note here is that there's roughly a 2-second delay between a power command and a power output, which explains the slight offset between the blue and the red curves here, blue being the measured output and red being the target. More interesting data is here, which is the battery and the wind turbine operating in parallel. I'll explain the graphs quickly before moving ahead. The top two plots are time series data of power, the target being in red and the measured value being in blue. The red value or the target is calculated based on the algorithm from a couple of slides back. And we've shown a shaded region here, which is the region in which the AGC targets are allowed to vary. So the shaded region is 80 kilowatts in total, and power always varies inside that region. You can see from a couple of statistical measures that we've used here that the error, at least with the data we have available, seems to be increasing with power level. Now, we don't have data at higher power levels, so we cannot confirm whether or not this is a sustained trend. An interesting aspect of this data is comparing it to the work we've done in the past. So I've put three sets of data in this table here, one with the battery operating alone. And as you would expect, the performance scores are fantastic. They're the highest of the lot here with the lowest error. When you add the wind turbine, the performance score drops as you would expect, and the error increases. However, relative to using only the wind turbine, the combined system does perform better. So you can see that the performance scores are higher and the error is lower, meaning that the battery does present a net gain. The question here ultimately is this profitable? Now, given PJM's compensation structure, yes, using the battery and the wind turbine to provide AGC is profitable as opposed to using the wind turbine to provide energy alone. But the bigger question is, does all of this cost and additional effort justify the investment cost of the battery? Now, given the inputs we've used here, the answer is no. However, you could ask a question, how would you make it profitable, or what would it take to be profitable? Now, we've played around with a couple of numbers here. This is a quick and dirty analysis of the level of performance you need to justify the investment cost of the battery. You can see that it is possible. However, you will need to up the regulation bid magnitude to 300 kilowatts and also increase the performance score to 92%. Now, 92% is not unattainable. It is feasible provided you are able to overcome challenges like communication delays, measurement errors, and make the algorithm a little bit more sophisticated. So, at the end, we'd like to thank our sponsors, the Alberta Electric System Operator and the Saskatchewan Research Council for technical support, and Natural Resources Canada for their funding, and also Enercon Canada for providing technical guidance and support with their wind turbine. Thanks for your time. I'm available for questions.